In this video, we will be learning about accuracy and precision. The learning objective for this video is to determine the accuracy and precision of sets of data. Accuracy refers to how close measured values are to the actual value. So for instance, if you're trying to make a target, accuracy refers to how close is the data to the center of the bullseye here. We obtain accuracy by buying equipment from reputable dealers and from calibrating our equipment on a regular basis. Calibrating refers to making sure that our instruments are recording numbers and data close to the true values that are accepted. Precision refers to how close a series of measurements are to one another. In other words, how reproducible is the data? And so precision here, this is low precision because the data points are far apart. Here, this is high precision, but low accuracy. Precision means that they are close together, even if they are low accuracy, meaning they are far apart, far away from the true value. Ideally, we want our measurements to both be precise and accurate. So ideally, we want to be here with high precision and high accuracy. Precision does vary by which equipment we are using. In the lab, we never use beakers to actually measure out volumes because they are so low in precision. And so we never want to use beakers for actually measuring volumes. These are just for approximate measurements. Graduated cylinders are a bit better because the lines are typically a bit closer together. But when we need even more precision, then we have to go with a burette or other device that has even finer tuned lines. So you can tell the precision of the instrument by how close together the lines are. The finer the increments, the more precise the instrument is. So in the speaker, the lines are 10 milliliters apart, and so our estimated digit is in the ones place. Remember, we're allowed one estimated digit and only one estimated digit. And so since our estimated digit is in the ones place, we can say that our measurement is within plus or minus 1 milliliter because that's in the ones place. Our estimated digit is in the ones place. For our graduated cylinder, our estimated digit is in the tenths place because the ones place is known. And so our estimated digit is there. Whatever place the estimated digit is in is where our precision lies. So our precision here is in the tenths place. And then for the burette, we know the tenths place, and because there's lines for it, the tenths place are known. And so the hundredths place is estimated. And so our precision is within the hundredths place for a burette. So this is more precise. This is less precise because we have more precision as we make our increments smaller and smaller. Now, when we look at a set of data, we can try to decide whether the data is accurate or precise, or ideally accurate and precise. Below are sets of data for 3 different students who were trying to measure a lead block with a true mass of 10.00 grams. How close which students were accurate and which students were precise. After you figure that out, we'll look at graphs of data to figure out if they were actually accurate or precise or both. But go ahead and pause the video and try to think about which students were accurate and which students were precise. Okay, let's look at graphs of the data. Oh, too far. Okay. So if we look at graphs of the data here for student A, we can see that the true value here, indicated by the blue line, is 10.00 grams. Some measurements are much bigger, some measurements are lower. There's a pretty wide range, and so we're going to say that that's not precise. So there's a wide range to the data, and so that's not precise. And also, since it's kind of varying like 10, like way above to like pretty far below the true value, it's also not accurate. For student B, all of the measurements were really close together. And so it is precise, but it's still not right on that 10.00 line. It's still, all of these are below. Student C, all the measurements are really close to 10.00. And there's not a lot of fluctuation. All of them are just really close. And so it's both precise and accurate. Now, just how far apart you are from the true value to make that decision about whether you're accurate or not, that we will be talking about in lab and defining that a little bit better about which data points you keep and which data points you need to throw out or remeasure. But for now, if it's substantially far away, it's not going to be accurate. As far as types of errors go, we have two different types of errors that we will talk about. We have random errors, which refer to fluctuations around the true value, and we have systematic errors, which mean consistent departures from the true value, which indicates a calibration problem, meaning our instrument is just off from the true value by some amount. Random errors, they're going to be some above, some below, like student A. So student A had random errors. A lot of times random errors indicate a problem in the technique being used. Like the student is not being super careful about each trial, because really you shouldn't have this happening. Like you shouldn't have almost a milliliter difference or gram difference between the two values. Student B, all of them were very precise. So here, random errors, you won't be accurate and you won't be precise. If you are inaccurate but precise, you're most likely in the systematic error. Because all of these measurements are really close together, they're just offset from the true value. So that indicates that this balance was just kind of offset from the true value and it needs to be recalibrated. Systematic errors can be difficult to detect if you are not calibrating your equipment on a regular basis, because all of your measurements will be close together. They just won't match up to the true value. And so unless you record what the true value is, you won't realize that something's wrong. Student C, their balance here was recording all of the masses very close together, and it's very reproducible data. Um, and so these have little to no errors, and so it doesn't fall under the random error or SMAC error. So small. There is a little bit of randomness to it because some are above and some are below, but small errors, if any, a little bit random, but very small.